Okay, so let's chit chat about the lab from yesterday, because that's gonna tie in a whole bunch of different things. So your first kind of big test is going to be tomorrow. Okay? I guess like I haven't told you all this. So there's nothing new to learn. So it's just all an application of what we've been doing. So let's talk about the lab from yesterday. And these I promise you, big portion of this test tomorrow is going to be able to do these molarity calculations. Okay, I promise you. And there's three types of molarity calculations. The first one is like this, and because that's the most practical. I'm going to say, hey, I'm in the lab, I'm setting up the chemicals, and I need a certain molarity and a certain volume. Okay, so the cool thing about copper sulfate and all copper ion solutions is that they have a distinctive blue color to them. Whether it's copper nitrate, it's copper sulfate, doesn't make any difference. They all have a distinctive color. So that's why we use this one. I couldn't have done that lab with that spec 20 with like sodium chloride, because salt water is just clear. Okay, there would have been no bears to intercept the tinnies. So with that, with a saltwater solution, you would have never seen any change in the amount of light that's being transmitted through. It all would have just been the same. So that's why we use copper sulfate, because copper sulfate has a unique ability to have color. So remember, when you see something, it's because photons are hitting it and it's bouncing off. So basically, what you did, and this is the one calculation you have to be able to do without fail. I'm going to say, hey, I want to ask you to prepare a certain calculation. I'm going to say, hey, I want 100 milliliters of a 0.5 molar solution of, say, I don't know, potassium chloride. Okay, so this is a calculation you have to be able to do without hesitation. Now, let me give you a hint about how to prepare for this test. Anytime you know, hey, here's the type of calculation that you have to be able to do. Okay, you've done them like in that packet that you all have. There's a whole bunch of ones. You have the videos, you can watch the videos. You have all the resources in the world. You have to be able to do these again and again and again until it just becomes second nature. So like, let's say for example, you play tennis, okay? You're not gonna sort of throw the ball up, hit it one time and go, okay, hey, I'm good, I'm done, all right? This has to become repetition. Any math class, any science class where it's calculations, you have to do these again and again and again and again and again until, wow, I got this. Then you sit back and think, okay, let me change the numbers. What if I made that a 1 molar solution? What if I made it a 200 milliliter solution? What if Bergkamp gave me that volume in liters? Okay, that's what you have to do. When I was taking like kind of like one of my advanced physics classes, I'd actually write my own tests. And I'd say, okay, if I were the teacher, what questions would I put on that test? And that gives it a whole different perspective about how do you prepare. It's like, oh, what would I ask on this test? You all have been students long enough. You know how the game is played. Ask yourself, what would I ask? Things like that. So here's what you got to be able to do. And here's the main idea. Will the scale measure in moles? No. So Grace, what do you know? What's one thing you know you're going to have to do with those moles? Convert it into grams. And anytime you convert moles to grams, where are you going to look to find that source of information? Periodic table. So you know. Okay, so I said, oh, hey, what are some things you're going to have to do? You know, one of the things you're going to have to do, you know you've got to convert moles to grams, because that's what the scale measures in. You know at some point you have to look at the periodic table. Okay, you know those are two things that have to happen. You know that at some point, what do you want your final answer to be in? Fundamentally, what are you going to have to figure out? Grams. So at some point, you know your final answer has to be in grams. So if you can think through that process and go, okay, hey, what are some things that I have to do? Some people like to make index cards. They'll say, okay, hey, here's a solution prep problem. How do I do that? Okay, let me write down the steps so that if you force yourself to think through that, it's called developing an algorithm. If you force yourself to think through that algorithm and go, hey, how do I think through this process? Okay, and it's called metacognition. And it sounds weird, but you think about how you think. Okay, it's like, how do I solve this problem? What do I have? What information do I have to have? What steps am I going to go through? So if you think about what you think about, that can sometimes give you some deeper insight into the problem. All right. Now, here's the other thing. The most important part of any molarity problem, and I cannot emphasize this enough, when you see 0.5 molar solution, at the end of the day, what does molarity mean? In what units is molarity measured? Moles per liter. So what this means is that we need a half a mole per liter. Okay, at the end of the day, you have to start with this idea. I have moles per liter. This is what this means. Okay, I'm going to take a half a mole and I'm going to dissolve that in 1 liter. Okay, but here's the problem. I don't have a scale that measures in moles, and I don't need a liter. So I got to get rid of the moles and change those into grams. And I've got to get rid of the liters so that I just have grams. And again, here's the two ways you can do this problem. One option is that you just work it all in one step. You say this is 0.5 moles per 1 liter. So you come down here and you put 1 mole, and then you're going to have, what did I say, potassium, 1 mole of potassium chloride. Now, when you're finding these molar masses, and you will have that laminated periodic table, okay? That's what you're going to have on the test tomorrow. You just have to know how to use it, okay? So, when you're writing down these molar masses, so you got to be able to do this without fail. What's the molar mass of potassium? I know chlorine's 35.5. What's potassium? 39.1? Okay. And go out to at least the tenths place. Okay? So we're going to add this together, we get 6, 14, 74.6. Now, if I just stop right now, okay, and think your way through the various steps of this problem. If I stop right now, I have grams per liter, okay? And if I were to mix up an entire liter of this stuff, this would tell me how many grams I would need. But I don't need that much. I'm only going to mix up 100 milliliters. So you can take the 100 milliliters. Oh, there's 1,000 milliliters in 1 liter. You divide, you get 0.100 liters. So then look what happens. The liters cancel out, the moles cancel out, you get grams. So when you answer this question on the test tomorrow, you're going to say, I'm going to dissolve, by the way, somebody take a calculator and do this math. Let's get an answer. Take 0.5 times 74.6 times 0.1. 3 point what?
73.
Grams of and 100 milliliters of water. Okay? There you go. So that's just how you're going to answer this. When you do that mass, okay, you know the scales that you're using by now. There's 2 decimal places to the right. So when you're doing that mass, have 2 decimal places to the right. because that's what your scales can measure in, okay? Now, that's one way you can do the problem. The other thing that you can do, and you do the same math, but some people like to work this as a ratio. You go, okay, hey, I need a half of mole per 1 liter is going to equal X number of moles over 0.1 liters. Okay? You can set it up as a ratio and go, oh, okay, bless you.
Thank you.
So I'm going to take 0.5 times 0.1, and I'm going to get 0.05 moles. Okay? That's how much I'm going to need. Okay? Because if I need a half mole in 1 liter, I'm going to need 0.05 moles in 0.1 liters. Oh, I'm not going to need as many moles. Then you can sit there and go, okay, well, 1 mole is whatever that 74.6. Moles cancel out. You end up with the exact same answer. You just have to come up with a thought process that makes sense to you. Okay? I don't care. Literally, I don't care. But you have to be able to work that problem. And on the test, when I give you this big blank area, that's where you've got to show me, hey, Burkamp, here's my thought process. This is what I went through. These are the steps to get to that answer. Okay? So the only thing that will ever change, if you think about this problem, the only thing that you will ever change is this, depending upon the molarity. You're going to change this, depending upon what chemical it is. And you're going to change this, depending upon the volume. Okay? So if you want to, some people, like I said, they live for flashcards. And you would make up like an index card or something. It's like, okay, how do I prepare a solution? I'm going to put given molarity here over 1 liter. I'm going to put 1 mole of given down here. I'm going to put the molar mass here. And I'm going to put the needed volume here. Okay? So if you want to make it up an index card and say, oh, how do I prepare a solution? There you go. The only thing, and I would give you this, you'd have to look at the molar mass, and that's the total needed volume. And if you like that, go with that. You go, oh, this is how I do these problems. Okay? And then what some people would do is called, there's different names for it, but I always like the splashdown method. So, because what some people do is like, they'll come into the test, they have all this information in their head. It's like, okay, I got this number, I got this. And what they'll do is they get the test, and they will just like offload this information. They will just they'll get the test and they'll write this down. It's like, okay, I don't have to think. Now, if I have that, I can offload that information. I'll write that down on the front of the test. And then when I get to my molarity problems, I'm going to go with that. That way, I understand that. Okay? Now, personally, I would prefer that you actually can think through the process. But if this works for you, go with it. Okay? You just have to figure out, how do I think through these problems? Okay, so that's one molarity problem you got to be able to do. Now, the second molarity problem you got to do is that I'm going to give you information and you're going to calculate the molarity. So let's use this, we'll use the potassium chloride, so we already know that molar mass. 74.6 grams per mole. Okay? So I would say, okay, I'm going to give Raman 4 grams of potassium chloride, and she's going to dump that into 250 milliliters of water. And I want her to be able to calculate the molarity. Okay? So basically, we're going to make the door swing the other way. So here's the other type of problem I'm going to expect you to be able to do. I promise you, mark my words. Okay? These are problems you've got to be able to do. So, Ella, what am I going to have to do with the 4 grams? Cough, cough. Ella, What's molarity measured in?
Moles per liter.
Moles per liter. I have grams.
Okay, so moles.
Okay, I gotta change the grams into moles. And then I'm gonna have to take the milliliters and change those into
Liters.
liters. Okay, so those are the two things I gotta do. I gotta change the grams to moles and milliliters into liters. So, since I'm trying to find that molarity, again, if you just remember, oh, that's moles per liter. Those are the two bits of information that I have to have. I gotta have how many moles I'm gonna have. I gotta figure that out. And then I gotta divide that by the total volume of liters. Oh, okay. So I'm gonna take 4 grams of potassium chloride. I know that's 74.6 grams in 1 mole. So that will give me the number of moles. That's a conversion you have to be able to do without, like, falling off of a log. Okay, oh, grams to moles, no worries there. So that's gonna get me a certain number. You know, there's 250 milliliters. Well, there's 1,000 milliliters in 1 liter. That becomes 0.250 liters. So I'm going to take 4 divided by 74.6, get the number of moles, divide that by 0.25, boom, there's my molarity. Okay? Second type of problem you've got to be able to do without a thought. Now, the third type of problem you're going to be able to do. I'm going to give Parker, I'm going to give him 10 milliliters of a 0.6 molar solution of sodium chloride. And I want him to be able to tell me how many moles of sodium chloride I have within that. Okay? Now, Parker, you want an answer in moles. That's it. Okay? Moles. But molarity is in what?
Moles per liter.
Moles per liter. So what am I going to have to do to get an answer in moles?
Multiply by your liters.
Yeah, I got to get rid of the liters. Okay? The only way I can undo moles per liter and get rid of the liters is multiply by liters. Okay? That's it. Now, here's the deal. And think this through. If I gave Parker an entire liter of this stuff, he would have 0.6 moles. Okay? We don't have an entire liter of it. I'm only going to give him like 10 milliliters of this stuff. This is a very small amount. So I'm going to have a lot less than 0.6 moles, because again, that's what that number means. So you got to be able to take the 10 milliliters. Oh, there's 1,000 milliliters in a liter. That's 1 liter. So if I multiply that by 0.010 liters, the liters cancel out, I get moles, boom, there's my answer. Okay? So those are the 3 types of problems you have to do without thinking. How do you prepare a solution? How do you determine the molarity of a solution? And how do you find the number of moles in a given volume with a given molarity? Okay? Those 3, out, fail, boom. Now, a little bit of terminology. This is, I asked you this on the lab, and hopefully you all know this. When you're talking about solutions, you have 2 things. You have the solute and you have the solvent. I would assume, did they teach you this in middle school? Hopefully they did. Anybody? Okay, let's make it. I see some blank stares. So the solute is what you add. So like yesterday, you guys took copper sulfate and you dissolved it in the water. So your solute is what you add. So like yesterday, your solute would be the copper sulfate. Okay? The solvent is what does the dissolving, which in that case is your water. Almost all the time, what we're going to have, the solvent is probably going to be water. It's exceptionally rare that we don't use water as the solvent. Okay? The solute, that's what you add. The solvent is what does the dissolving. So when in doubt, the solvent's going to be water. Now, the other thing that you got to be able to do, and we've done this, is that you have to draw what's called a particle view. So if I said, hey, draw a particle view of what's happening. So when in the lab that you all just did. So if you want to draw the water molecules as like little Mickey Mouse people, okay, right? Because it's an oxygen and two hydrogens. So now here's what's going to be important, is that this stuff breaks apart into copper and sulfates, okay? Coppers and sulfates. So if I were to ask you to draw a particle view of what took place, this is what it would be. You'd have coppers, and you'd have sulfates, and you'd have water. Now, is this a mixture or an element? Once you add the copper sulfate, it is a mixture, an element, or a molecule. Multiple choice question. I've dumped the copper sulfate into the water. So is it A mixture, B, a molecule, or C, an atom? What's your choice? Alec?
Mixture.
Yeah, okay. So now, within the beaker, you have molecules of water, okay? You have molecules of water. But because of the fact that you're mixing the copper sulfate with the water, so it is a mixture. Now, is it a homogeneous mixture or a heterogeneous mixture? Parker?
Heterogeneous. No? Wait.
Okay, so here's the deal. So if you look at what's happening, heterogeneous would be like if I take my pen and I dump it in there. Because then I'd have a solid with a solution. Homogeneous, heterogeneous.
Homogeneous.
Homogeneous, right? Air is a homogeneous mixture because everything's a gas, okay? Our atmosphere is a homogeneous mixture, okay? Heterogeneous is when you have like solids and liquids or solids and gases, okay? Like this room right now, if you consider this entire room, is this entire room a homogeneous or a heterogeneous mixture? Heterogeneous, okay? Because you have solids, you have gases, okay? We've got some water, okay? We have some liquids. It's very heterogeneous. Okay. So make sure that you can draw like a particle view. Now, one of the questions, speaking of which, this goes to question number on this back side, okay? And by the way, on number 1, let me give you a hint. On that first question on the back, when you're trying to find that molarity, and again, this is a problem you have to do without thinking. Your answer to number 1 should be, and this is an ish, okay? It's going to be somewhere between 0.3 and 0.5. Okay? That's going to be that molarity on number 1, somewhere between 0.3 and 0.5. If you ever get a molarity of like 24, that's a train wreck, okay? Top end molarity might be 18, and that's highly, highly, highly concentrated solutions, okay? Most time molarities are going to be between 0 and probably 2, okay? That's where most molarities are going to fall for the most part, okay? Certainly if you get a molarity of like 24, bad, stop, no, it's not possible, okay? Then on number 2, where you're going to mix up that sodium chloride, how many grams of each? So your mass of your sodium chloride, this is an ish, but your mass of your sodium chloride should be something around your age, okay? That's an ish, okay? That's a huge ish, but it's something around your age, okay? And the mass of the magnesium chloride should be in the mid-20s, okay? So that first answer is around your age, that second answer is in the mid-20s. Now, On number 3, it says, which solution will contain more particles? Explain your answer. So here's what you want to look at. So you've got sodium chloride, and then you have magnesium chloride, okay? So you have to visualize what's taking place when something dissolves. When something dissolves, you break the bonds that hold it together as a solvent, okay? So basically, the sodium floats off by itself, and the chlorine floats off by itself, okay? Now, when the magnesium chloride does that, you get one magnesium, but how many chlorines do you get? 2. So you get Cl and Cl, okay? So once they dissolve, and that's the whole key to answering question number 3, which will contain more particles once it dissolves? The magnesium chloride will, because it has 3 parts that break apart, 1 magnesium and the 2 chlorines. The sodium chloride just has 2 parts. It just has the sodium and the chlorine, okay? Your answer to number 4 is going to be a really small number, okay? And your answer to number 5 is going to be a really, 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 really big number. So your answer to number 5 should be something like 10 to the 23rd. On your graph, make sure that you have absorbance here, you have transmittance here. That should look something like this, okay? Because as your absorbance becomes like a bigger number, then you have less and less and less of that light that's going through, okay? Yes?
How do you find the theoretical concentration?
That theoretical concentration is either 1, 0.5, or 0.25. Yeah, those are what you should get. Those are your theoretical values.
Okay.
So make sure on that experimental error, so like, Emma, give me one of your, like, that 0.5, what did you get for the concentration off the machine?
0.45.
0.45? Okay. So if I'm Emma and I'm going to show this calculation of experimental error, this is what I would expect to see. First off, this is like an absolute value. So it's your theoretical. What it should be reading is 0.5. Like, who's the group that basically got them all spot on? Yeah. Yeah, you guys are like literally never seen, that was amazing. So anyway, so you can take 0.5 minus 0.45 divided by 0.50 and then times 100. So you're going to get like 5% or whatever that is. No, you won't get 5%. You're going to get 2.5, something like that.
0.5 minus
0.45.
divided by
0.5. No, it's like 10%. Hello. Yes? Okay, all right, thank you. All right. Barbara, you need to bug out at 8:45. Okay. Okay. Any questions on the lab? Going once? Going, yes?
I have so many questions.
Okay.
So many questions.
Okay, well, can you come in during encore? No, today, yes. I got a stupid testing.
No.
When they're working on that lab, I'll try and answer those questions. Okay? What, Miles?
I didn't get a graph paper yesterday, so can I, yeah. Thank you. Thank you.
What?
Do you want us to connect the
Yes,
dots?
connect the dots. Ideally, you connect the dots.
Starting at the origin or?
No.
Okay. I think
Because this
I'm
graph
fine.
this is like an inverse relationship. This does not start at the origin.
Okay.
So it should go something like this. Abby,
Wanting a line of best fit?
with the 3 points, yeah, you could draw a line of best fit. That would work. Okay, depending upon how screwed up your data is, it tends to
It's a
be,
little bit.
it tends to be pretty linear.
Yeah.
Yeah. Grace,
So where's it coming from on the transmission line?
what do you mean?
Like
Your transmittance goes from 0 up to 100. Your absorbance goes from 0 like up to over to 1. Okay, so yeah, your absorbance scale is gonna go from 0 to 1, and your transmittance line is gonna go from 0 to 100.
So the line is coming from 100 on the.
Well, no, you're just gonna have your few data points. So I'm guessing your data points might be like here, here, and here, something like that. So,
Draw lines.
Absorbance.
yeah, you can just draw a line through those 3 points.
Oh, okay. So point one was at 70.
Well, but divide, I get 3.75
Okay.
Okay, anything else?
Wait.
If you want to wait while,
No, never mind. Got it.
okay.
Yep.
If you want to hold on to this lab and hand it in tomorrow, you can. Okay? If you're done with it and you're feeling good, you are likely to see a question about transmittance and absorbance on the test. Okay? So just realize that the more dilute the solution is, there's fewer bears to catch the timmies. Okay?
Tim's.
And have your visual about absorbance and transmission. Okay, so Miles, stop that for a second. Okay.
You dropped your alarm.
I did. All right. So this lab that you're gonna do is kind of cool. It's like a practical. So what I'm gonna do is that I'm gonna give your group a sheet of aluminum foil about like you did, okay? And there's a whole bunch of things that you need to figure out about that aluminum foil. You need to figure out the total number of aluminum atoms that are within it, okay? Now let's just think this through. You're gonna have a sheet of aluminum foil about like you. You're gonna find the total number of atoms in that piece of aluminum foil. You think that's gonna be a really big number or a really small number? Small, big. Big, right? There's a whole bunch of
Oh, never
atoms,
mind. Sorry.
right? There's a whole bunch of atoms in that aluminum foil. How do you know there's a whole bunch of atoms in it? Atoms are really, really small, right? Okay? So that's one of the things you're gonna do. You're gonna find the thickness of that aluminum foil, but you can't measure it directly. Now let's think this through. Pretend that you're in a math class. If I gave you a block of wood like this, how would you calculate the volume of that block of wood?
In terms of what's going on.
Right? So your volume would be length times width times height. True? True. So if you can figure out the volume of the aluminum foil, okay? And if you know two of the dimensions, you can figure out the third dimension. Okay?
What? The height, which is gonna be microscopic. Sorry, I think what? What?
What'd you say, Grace?
The height, which is gonna be like microscopic, because it's aluminum foil.
Exactly.
I'm sure the ruler is.
Now, this is also going to involve density. I'm going to give you the density of the aluminum foil. So if you know the density of the aluminum foil,
Figure it out yourself.
and you know the mass of the aluminum foil, which you can find, how are you going to find the mass of the aluminum foil? Put it on the scale. So I'm going to give you the density. You can find the mass. Knowing the density and the mass, you can find the volume.
Oh, my God.
And then if you know two of the dimensions, you can figure out the,
Alright.
okay? See where this is going. Now, what you're ultimately going to try and figure out, and I'm going to draw this really, really big. You're going to try and figure out how many aluminum atoms there are stacked side by side by side to equal the thickness of that aluminum foil. You're going to figure out how many aluminum atoms that's going to take. Okay? Hold on, we'll get there.
What?
We'll get there.
No, I'm English.
Why? Because I'm gonna make you think?
No.
That's true. Okay. So, here's the deal. So let's say that we have two different sized particles. We have this little white marble and we've got this bigger red marble. And I want to figure out how many of these it would take stacked side by side by side to equal the width of this paper versus this one stacked side by side by side. So how could you figure out that information? What would you have to know?
Size of the particle.
What'd you say?
The size of the particles.
The size of the particles, right? So we're going to assume that the aluminum atoms are round, okay, right? Or in this case, round. So there's two things you can measure. You can measure the radius, or if you double that up, you can get the diameter. Okay? Now, think this through from a units perspective. Let's say that this is 1 centimeter diameter. Okay, let's say it has this is 1 centimeter. So this small one has a diameter of 1 centimeter. Okay? And let's say that that paper is 20 centimeters across. So that paper is 20 centimeters across, and the diameter of this is 1 centimeter. How many of these would it take? 20. How'd you get that? Now, think through the algorithm. What did you divide what by? What's the 20 centimeters represent? Yeah. So you're going to take whatever that length is, right? Then what did you divide it by? Yeah, the size of the distance per particle, right? So you divided that by the distance per particle. True? Now, in this case, those particles are marbles. Marbles. I lost my marbles. Okay? Now, look what happens. This is where the magic happens. If that length is in centimeters, and you divide that by centimeters per marble, guess what? That's like taking centimeters and multiplying that by marbles per centimeter, multiplying by the reciprocal. Look what happens. The units cancel out. You get marbles. Okay? That's the same thought process that you're going to do to figure out how many atoms it is thick on that piece of aluminum foil. So if you can figure out the thickness of the aluminum foil, and if you can figure out the diameter of each aluminum atom, you can figure that out. Now think this through. When you stack those atoms side by side by side to get the thickness of that aluminum foil, do you think you're going to get a large number of aluminum atoms or a small number of aluminum atoms?
Large.
Pretty big, okay? You're going to get a pretty big number of aluminum atoms, okay? So, stop that. So, here's the information that you have. The density of aluminum, 2.70 grams per cubic centimeter. Notice that has 3 digits in that value, 2.70. The other thing I'm going to give you is, this is going to be important, the radius of an aluminum atom is 118 what we call picometers, okay? Picos are extremely, 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 extremely small. And I give you that if you have 1 picometer, that's 1 times 10 to the negative 12 meters, okay? So in other words, if you have 1 meter, that's like 1 times 10 to the 12 picometers. So what that means is that each picometer is really, 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 really small, okay? So it's going to take a whole bunch of picometers to equal 1 meter. Then, here's what you're going to have. You're going to have a scale back there, okay? I'm gonna give you a piece of aluminum foil, and that's it. Now, you're gonna hand in one write-up, and this is gonna be due on Monday, not tomorrow, okay? It's gonna be due on Monday. Today, if you can just get the data and come up with the thought process, that's cool. You're gonna hand in one per group. If you wanna create a shared document and type this stuff up, you can. If you just wanna write it out old school, you can. But here's what I'm gonna be looking for. There's 3 things that you're gonna need to tell me. The thickness of the aluminum foil, and you cannot measure it directly, you have to indirectly find the thickness of your aluminum foil. The total number of atoms in the aluminum foil, okay? And how many aluminum atoms thick the aluminum foil is, okay? So those are the 3 things that I want. So you can set this up in sections and go, here's this calculation, here's this calculation, here's this, okay? So what you're gonna try and do, and this is what I'm gonna tell you, this is what I want handed in, a clear, concise, and repeatable procedure. So what you're gonna do is that you're gonna write up a procedure, and this doesn't have to be anything complex. You're basically gonna say, hey, here's what we wanna do. We're gonna do this, we're gonna do this, we're gonna do this, okay? That might only be 4 or 5 steps long, okay? But basically what you're gonna try and tell someone is you're gonna try and tell a Chem 1 honors student that's not in this class, hey, this is how we found it. So if someone gave you this challenge, this is the thought process that you're gonna go through, okay? Any data that you're gonna have, so if you wanna set up like a data table, say, hey, this is what we measured, okay? So this is just the raw data. Here's the mass, here's this dimension, here's whatever, okay? Whatever data that you need to collect. Then the whole point of this is what I'm gonna grade you most on is the thoroughness of your calculations, okay? I want to see the numbers. I want to see formulas. I want to see units. This is like your lab final for this whole thing. You're only handing in one per group. I can't tell you how much your grade is going to be based upon how impressed I am, okay? So if I just see, let's say, hypothetically, none of you would do this, but let's just say, I see 0.5 divided by 2.7 equals 0.04. And let's say that's all I see. How happy am I going to be? I will flip out, okay? Number one, I'd have no idea what this is. There's no units. I have no idea what this is, okay? It's train wreck, okay? Horrible, horrible. If you put down a number, there better be units with it, okay? That's kind of your general rule. If you put down a unit, there better be units with it. So, down here I tell you exactly how I'm going to grade this thing. Quality of the writing technique and the procedure, okay? Do not write this as a paragraph. You do step 1, you do this. Step 2, you do this, okay? Measuring techniques, okay? The scale, you know that's going to go to the tenths and the hundreds. When you measure things on the aluminum foil, are you measuring out to the correct place value? Thoroughness and details of the equations and units used throughout the process, okay? Numbers without units, bad. Correct use of significant figures. So if you look on everything you're going to measure, you're basically going to have 2 or 3 digits, okay? That means every calculation that you do should have 2 or 3 digits. Overall impression, okay? I want to be impressed. If you want to include some art, diagrams, things like that, again, I don't impress easily, but I want to be impressed. This is like your culminating lab final. So, as you prepare for the test tomorrow, okay, you have that entire packet. And here's what I want done in terms of what I'm going to grade. You all have that big packet. So let me make sure. There's a lot of that stuff that we did is like supplemental stuff. So the only thing that you have to have that I'm really going to go through is through the bottom of page 10. okay? You're gonna hand that in, but through the bottom of page 10, and then, whatever page was that? And then, so what you have to have done is anything 1 through 10, and then questions 17 through 21 on page 19, okay? So out of that packet, that's the only thing that I really have to have done. Now, if, again, you have videos there, there's like a molarity lab, there's on page, what page was that? On page 13, there is a whole bunch of calculations there, and you have the answers, okay? You can do, you don't have to do those, but if you do them, this is basically what you can do to review for the test. Be able to determine and know your vocabulary. How is molar mass different from relative atomic mass? But how are they related? So if I tell you that the relative atomic mass of nitrogen is 14.0, okay, atomic mass units, okay? Remember, that is not, let me make sure everybody's cool with this. That is not a direct measure of the mass of a nitrogen atom, okay? All that's telling me is that that's a little bit more massive than a carbon atom is. So when you see atomic mass units, that is not a direct measure of the mass of a nitrogen atom. If you want the actual mass of a nitrogen atom, so if you have 1 mole of nitrogen atoms, you have 6.02 times 10 to the 23rd, right? Atoms of nitrogen. So within this sample, you've got all of these billions upon billions upon billions of nitrogen atoms. And if you add up the mass of all of that, that adds up to 14 grams. And I promise you, I'm going to ask you, what is the relationship between Avogadro's number, mass, and relative atomic mass? And you better be able to tell me that 1 mole of anything contains 6.02 times 10 to the 23rd particles, and the combined mass of all of those particles is equal to the relative atomic mass in grams. Okay? And you have to put the in grams on the end of it, because pounds would be something completely different. I promise you, I'm going to ask you that question. Just as if sure as the sun rises in the east tomorrow morning, I'm going to ask you that question. Now, if the sun doesn't rise, we're going to have other issues. Okay? Like we've lost our sun. This is bad. Okay? We'll have other issues. Okay? But assuming that the sun rises tomorrow in the east. Okay? I'm going to ask you that question. I promise you, okay? Make up a card. Get a piece of paper, whatever. Tattoo it on your friend's forehead. That might be a bit extreme. But you know you're going to have to tell me the combined mass is 6.02 times 10 to the 23rd particles equals the relative atomic mass measured in grams. I promise you. It was on a worksheet that you've already done. I promise you I'm going to ask you that question. So, if I take 14 grams and I divide that by 6.02 times 10 to the 23rd, that's going to give me the mass of 1 individual nitrogen atom. If I did that for aluminum, the atomic mass of aluminum is 27 grams, 6.02 times 10 to the 23rd. So, if you find the mass of an aluminum atom, guess what? That's going to be bigger than the mass of a nitrogen atom, which is why if you have a mole of nitrogen, that's only 14 grams. If you have a mole of aluminum, that's 27 grams, because aluminum atoms are bigger than nitrogen atoms. Okay? I promise you I'm going to ask you that. Know your terminology. Solute, solvent, heterogeneous, homogeneous. Okay? The difference between an atom and a molecule. Okay? Know the difference between those. Atoms combine to make molecules. Okay? What's a mixture? What's an element? That type of thing. Know your vocabulary. Okay, I'm done. You have half an hour. The data that you need is going to be pretty simple to get. Okay? Literally, it will take you not a lot of time to get the data. The calculations with the data is gonna take some time. Now, I'm gonna tell you right now, the toughest part of this lab is gonna be the thought process on figuring out how many atoms that you stack together, okay? That's gonna be the toughest thing. So, think back to the analogy with this paper. I have these, okay, versus these. So if I gave you the diameter, think through that thought process. How did we do that? Okay? Think through the thought process. Pay attention to these. Okay, so I'm done. Stop you on the camera.